All right, now that we're starting to get a little more comfortable with the code to compute these audio novelty functions, I want to see if we can improve them a little bit by changing the choices that we make when we look at the difference from one column to the next. First, though, I want to assess what we've already done by listening to it. We can actually turn this thing into a sound that we listen to and then try to hear what information it's picking up on. And so this is a theme that we're going to see throughout the next few units, where we develop features for audio. So this is called a feature. We're going to listen to the features and see what information did they preserve about our audio. So what I'm going to do is create just some noise that's 10 seconds long here, but I'm going to make the amplitude of the noise be proportional to what the value of the audio novelty function is. So let me make a function here, or a method. I'll call it Sonify nav function. So it'll take in an audio novelty function. It also needs to take in a hop length, because I need to know the number of samples in between each element of the audio novelty function. So what I'll do is, okay, I know I need to make an array X. It should have as many elements. So I'll make it random. So np.random.random. So I'll start as noise. It should have as many elements as the number of elements in the novelty function times the hop length, right? Okay. So this is just random noise, but how do we make it sound like the audio novelty function? Well, let me go through and multiply each slice that occurs over an interval for one of these samples and multiply it by that sample's value. So I'll say for I in range length of novelty function. So I'll say X from I to, or I'll say X from I times hop length to I plus 1 times hop length. Multiply that, scale that entire chunk of the random audio by the novelty function at that sample. Okay. Now actually it turns out if you get really fancy you can do this without a loop too, but for now I want it to be clear that what I'm doing is creating a bunch of noise and making the noise be louder when the audio novelty function is higher, and make the noise quieter when the audio novelty function is lower. So I'm going through every sample in the audio novelty function. I'm using that to scale an entire little chunk of audio that we'll hear. All right, so what I'm going to do is run this method. I'm going to say y is equal to sonify. Oops, I spelled sonify wrong. Sonify, so create a sound from the novelty function and the hop length, and let's listen to it. So this is the thing we're going to be listening to. Okay, there we go. So this is probably going to get this video flagged for copyright on YouTube, but I want you to hear the original audio so you can remember and pride yourself.
Come grooving up slowly.
Okay, so have that in your mind, and then here's what the audio novelty function sounds like. So you can kind of hear the beat. So you can hear the beat. I mean, it lost all information about the timbre and the notes, which was not surprising because we threw out, when we summed down the frequency axis, we threw out all information about the frequencies, but we're just looking for changes. So I use this to shape my noise. And it kind of sounds like it's picking up on a beat. Okay. But we can make this a little better. We can refine this idea a little bit. We notice that this is a little bit noisy. I know it's shaping noise, but actually the thing itself is noisy because, we would like it to really just peak on the beats, but you see that it has some high values in the middle there. So one of the things we can do is actually, I don't really, so right now, so I'm taking the absolute value of the amplitude at a particular bin minus the amplitude at the next column at that bin. But if I look at the original spectrogram, when a beat happens, it's when something was low and then it went high. So, but this would also pick up, because it's the absolute value, it would also pick up on stuff that's high and then goes low. But we really want the former. We want audio onsets. That's when the beats happen. So we don't actually want to include something that goes from high to low in the sum. So instead of doing the absolute value, what we should do is say, anytime we're going to do something where we say, look, everything that's less than 0, just make it 0. So we don't actually want to include things that are less than 0 in our sum. Because that means that the amplitude actually went down. We do not want that to contribute. We only want things where the amplitude is going up to contribute. So let's look at the difference there. Okay, you see how this really made it much clearer. You can see it in both this image and this image down here. So let's listen to this now. Good. So the beats are much clearer now. So that's all right. So I'm just going to have you do a quick exercise where instead of doing onset, you do offset. So when does the beat stop happening? So the beat claps, and then when is that clap finished? And then we'll move on and talk about how to use these cleaner images to estimate tempo.